I did my PhD at the University Telecom Paris, and worked with my supervisors Roland Bardot and Gaël Richard. And I had a 6-month secondment at the company Audiodynamics in Paris, and worked there with Clément Douard, who was actually also involved in the rest of my PhD project. So I'm concerned with audio source separation. Just briefly, what it is. Well, most music signals we listen to, they contain the signals of many different instruments, right? That's one reason why music is very rich and very interesting. Many instruments are playing together. And since the signals are mixed, we call, when we work on music source separation, we call those signals a mixture. However, for many use cases, it might be necessary to access a signal, an individual signal of one of these instruments in isolation. For example, you want to maybe listen only to the, or you want to remove the singing voice if you want to do a karaoke version of the song, or you want to extract only the singing voice if you want to transcribe the lyrics, or you want to extract the piano if you want to transcribe automatically maybe the score of the piano. And that's what audio source separation is doing. It takes as input a mixture signal, and as an output, we want to provide the signal for each of the instruments individually. And in my project, I'm mainly concerned with estimating the singing voice from a mixture. And there are many ways how you can do source separation. And so for singing voice separation, the best performance today is achieved with data-driven methods, which means at the moment, of course, deep neural networks. And quickly how this is done, well, we have a data set of labeled data. Labeled data in source separation means we have a bunch of mixtures, and for the mixture signals, we have the isolated source signals in isolation available. So for example, I have some song and I have the singing voice in isolation. And then we can train our deep neural network, our DNN. It takes as input the mixture, we estimate our source, for example, the singing voice, and then we can compare this with a cost function to the true, what would have been the true singing voice, and accordingly we will update our network. And if we do this often enough, in the end, we get really good estimates. So yeah, there are some things that are really great about this procedure. First of all, we need to make very few assumptions, so the risk of breaking any assumptions is also quite low, and in general, we need very little domain knowledge to do this task, because we try to explain everything by the data. And as I said, we can get really, really good performance with that. However, there are also some aspects which are less good about it. So these methods are quite inefficient. One inefficiency is regarding the data. We really need huge amounts of such data sets to get good performance, and also they are computationally quite expensive. However, now when we work with music, such data sets with mixtures and corresponding isolated sources are very difficult to obtain. First of all, music underlies copyright restrictions. So already mixture signals can actually be difficult to obtain and to use in a commercial product, for example. And then to obtain these isolated sources, that's also very difficult because they are normally not distributors. Artists, they don't want to share only their singing voice recordings without the instruments. And from some music styles, those isolated signals, they might not even exist. So there's definitely a problem here. And at the same time, these data-driven methods, they ignore some knowledge that we already have. So for example, we might know how these sources look like. We might know that in music, most of the sources are harmonic. We might know how these sources have been mixed together, or we might even have some complementary data. For example, a musical score or lyrics transcript, something that tells us something about the sources we want to estimate. And at the moment, this is not used. And this is the motivation of my project. My goal was to integrate available prior knowledge that we have into data-driven methods for music source separation. And we did this in two different approaches. First, for singing voice separation, we were interested in lyrics transcripts as site information. Lyrics, they contain definitely some information about the singing voice we want to estimate. and they're much easier to obtain than audio signals, right? I mean, lyrics transcripts are all over the internet, and also a user could easily transcribe them. You don't need a specific musical training or anything, any specific skill to transcribe lyrics from a song. And here we are looking at a supervised setting. So we consider that we have a small amount of labeled data, and we want to use additional transcripts of lyrics to help improve the separation. And in the second step, we want to go one step further, and now we say, okay, what happens if we don't have any separated sources to do supervised learning? So we want to try to, can we learn actually the separation task only for mixtures if we exploit some prior knowledge? And here we use fundamental frequency information, and we use explicit source models. And basically these 2 points are now the outline of the rest of my talk. So lyrics-informed source separation, there we use exactly the supervised training pipeline I was just talking about, with the difference that we have now lyrics transcripts as additional input. And we should have a look now a bit closer at these 2 inputs. So the mixture is, of course, an audio signal, and lyrics transcript is basically just a sequence of some words, right? The first thing we do, we translate these words into phonemes. Phonemes can be thought of as the smallest sound units of a word. So, for example, hello has the sounds h, e, o, and phonemes are great because they are like a mid-level representation between just written text and an audio signal, because they're also just basically tokens, but they are referring to the sound, right, of the word. And now to use them for source separation, we have one small problem. We don't know when in our audio signal which phoneme is pronounced. So we know they are going to be pronounced in some way, but we don't know where exactly. And this is a problem that's called automatic lyrics alignment. When I started my PhD, there was no method that could, with enough reliability, align phonemes on singing voice that was mixed with other instruments. So as a first contribution, we developed a new deep neural network architecture for what we call weakly informed audio source separation. By weakly informed, we mean, okay, we have this lyrics information, but we don't know the alignment. And actually, our network can make use of this information because internally it learns to align the phonemes and the audio with an attention mechanism, while it's only been trained for source separation. So in this first publication, actually, we just made some proof of concept experiments where we didn't use text, but some other information just to test if this whole idea can work. Then in the second publication, we use text as side information, but to separate in the first step speech from background music. And why did we do this? So we were pretty sure that this whole system, this whole idea of using the text to estimate the voice has to work first on speech. And if it can work on speech, it can also work on singing voice, because speech signals are much better described by text transcripts, right? Because a speaker normally, the goal of a speaker is to transmit the information that's contained in some text. Whereas singing voice also is concerned with artistic expression. There's rhythm and melody that has a much higher importance than accurate pronunciation. So yeah, we tried this on speech and could validate that we can improve the separation quality of speech signals by using the text. And just to give you an idea, I was saying we learn internally to align. That means that inside this network, we learn a scoring system. So we have here on the left, we have the sequence of phonemes that's given to the network. And here on the x-axis, we have a number of audio frames. And the network assigns to each phoneme, at each audio frame, a score that should reflect how likely it is that this phoneme is pronounced in this frame. And this is our internal alignment representation. And another reason why we started first on speech was that there was no data set with music mixtures, the corresponding singing voice signals in isolation, and the lyrics transcripts. So now we wanted to move on to work on singing voice separation. So what we did, we took the most popular music or the most popular data set for musical source separation, which was MuseDB. And we transcribed the lyrics. And this can be also used for, I think it's a nice resource for many other tasks. So we made this publicly available under this DOI. And well, then we went on, did some experiments on singing voice separation with lyrics. And the first thing we realized, we need to improve the alignment procedure, because as I just said, singing voice is a bit more challenging. So we were actually then also integrating some domain knowledge into the alignment procedure. And this knowledge is just the fact that we know that the phonemes are pronounced in the right order from the left to the right. And also, of course, the audio signal proceeds from left to the right. So we know that this alignment needs to be monotonic. And we found a way to integrate this into the automatic alignment procedure. And so one contribution was then what's called a new monotonic attention mechanism. And since from this alignment representation, we can estimate the phoneme onsets, this whole thing actually is a new automatic lyrics alignment method that can align phonemes on singing voice that's mixed with other instruments. And we found that this is brings quite good results, kind of competitive with the state of the art, while we are using much less data. So state of the art alignment methods use more than 3,900 songs for training. And here we, with our small MuseDB dataset, we had only 86 songs. So that was quite nice to see. And then, of course, we were interested now, in which aspects can we improve singing voice separation using this text information. So one thing we had to find out is that, you know, learning this alignment jointly while training the network for separation is really great for the alignment task, but it doesn't work, or in this case, the singing voice estimate is actually not much improved compared to a non-informed model. So here we took then a sequential approach, where we first align our phonemes and audio with our alignment model, and then we train a new network, which gets as input, again, the mixture and the text, and also as an additional input, the alignment information. And then we can actually improve our voice estimates. And so to find out, well, what kind of information is actually derived from the text, we did a small experiment. And we found that the text is actually used as a very, very strong prior. So the network relies a lot on the text to derive its voice estimate. We tried to input white noise actually in the new network, but that was trained before, and gave some text transcript of some song. Here it was, "But She's Too Blind to See in My Car." It's a song from our MuseDB dataset. And also we gave some alignment information. And I just want to play you what's the output. So here's some white noise. Maybe you should lower a bit the volume, because white noise can be quite harsh. Let's see. Okay, that's just some white noise. And this is shaped into this, just by the information of the text. She's too blind to see in my car. So I think most of us could understand some of the words. So it means that only based on the phonemes, the model does already predict a quite substantial amount of a singing voice that would sing these phonemes. And we see, of course, that this helps in some respects. So yeah, we could show that this improves the general singing voice separation, and especially in some segments that are especially difficult. So, for example, some sounds like S or sh, they might spectrally look very similar to, for example, strong, very loud played cymbals in the drums, and that's sometimes quite challenging to separate from the singing voice. So text here helps a lot. Or sometimes you have that the singing voice is quite low compared to the other instruments. And also in these cases, text could help a lot. However, since we have seen that the estimate is quite strongly dependent on the text input. If you do some mistakes in the transcription or the translation to phonemes, or mistakes in your alignment, there's also the risk that you degrade your voice estimate. And these all these observations, the single voice separation part and the alignment part, led to a third publication in a journal paper. Yes. So now I would like to talk about the second part, which is unsupervised learning for musical source separation, where we just, in our database, we just have mixtures and we don't have the ground truth signals anymore. So our neural network we want to train for source separation gets just a mixture. And our strategy will be somehow to resynthesize this mixture signal so that we can compare it to the true mixture and accordingly update our neural network. So, and how are we going to synthesize this mixture? We use explicit differentiable and generative source models. So we assume we know the number of sources, and we model each of these sources with generative models, so that if we each of these models, they have some parameters, and if we estimate the parameters of all the sources correctly, we can just resynthesize for each source the signal. We can mix them together, and this should then, in the best case, give again the original mix. And just briefly, for these models, basically you can use any sort of source model you want, but we used source filter model because we want to separate singing voices. So basically we use the harmonics plus noise model for the source part, and this together goes through a filter. The details don't matter so much. And this model has a bunch of parameters like the fundamental frequency, quite important parameter, and other parameters. And so actually, we don't estimate the fundamental frequency with our deep neural network. Since there has been a lot of progress recently on multi-pitch estimation, we estimate the pitches directly from the mixture, and then automatically also assign each pitch to each of the sources. So it's basically instrument assignment, what has been addressed in the previous talk, which can be done automatically in many ways. So our neural network then knows already which source has which pitch, and has, based on this information, to estimate the rest of the parameters. And then at test time, when this is trained, when the network has learned to estimate all the synthesis parameters, we can synthesize each of the sources individually and use these signals as source estimates. That's one possibility. Another possibility is to derive from these synthesized sources some filters and filter the mixture so that only the wanted source remains. That's a more classical approach. We tried both, and yes, I want to quickly talk about the results. So we tested the system on choir separation. We have a choir with a soprano, alto, tenor, and bass singer. So 4 voices, which we want to separate. And actually, choir separation is actually a very good use case for our system, because choirs are normally recorded together, right? If you sing with other people, you perform in the same room, and if you have a performance, it's normally recorded together. So it's very difficult to get clean ground truth signals for one choir singer alone. I don't know what that. Anyway, and okay, I think you can still hear me. Yeah. Yes, so that's actually a perfect use case. And just to give you an idea how these signals sound like. Yes, and what we observed in our experiments was that what I said, synthesizing, we can synthesize the sources, or we can filter the mixture. And filtering the mixture leads to slightly better results. So I can show you actually both versions. So this is the filtering approach. Here we are separated just the soprano. And here is the synthesized signal. So you see, I think the noise content is a bit overestimated. And we compared this method to two baselines. So of course, we must not forget when we always talk about data-driven methods that there are actually methods who can do this task completely without learning, without any data. They just decompose the mixture, and especially given F0 information, fundamental frequency estimation, this can be done quite well. So we had, of course, as a baseline to use a non-negative matrix factorization model, but we could see that our approach actually works better. And also we used a supervised baseline. And surprisingly, we also even outperformed a baseline that has been trained with the ground truth sources. And I think that's because we use this F0 information very efficiently. But this baseline also got the F0 information. And another interesting observation is that we trained our model first on 90 minutes of choir singing recordings. When we reduced this to only 2.5 minutes, our performance did barely degrade. But of course, supervised methods, they perform not really good when they're trained only on 2.5 minutes of data. So that was another nice observation. And in general, as I said, this project enables now to use data-driven separation approaches for any music styles where we absolutely have no access to isolated source recordings. And lastly, we cannot only do source separation with this project, but actually we can also use the fact that we provide a complete parameterization of the mixture. Since here we have, each of the sources is modeled with a parametric model. You can also access all these parameters in the end, and for example, do some style transfer. You can edit the fundamental frequency of one source. You can maybe correct, I don't know if there was some pronunciation mistake. You can do all sort of editing afterwards by accessing all these parameters. And yes, to conclude, the goal was to integrate prior knowledge into data source separation methods. We did this first by using lyrics transcripts for supervised learning, for singing voice separation. This has led to a new lyrics alignment methods. And we could see also that we can improve singing voice separation in challenging scenarios. And in the second part, we used F0 information and source models as prior information for unsupervised learning. And we developed a very data efficient methods. And yeah, here are my publications. One paper, the unsupervised paper is actually just in review right now. Thank you very much.